Okay, this video is going to deal with induction and EMF. Okay, so magnetic flux. Magnetic flux is the measurement of the strength of the magnetic field per unit area. So I have a certain area, and there's a magnetic field in here. How strong is this magnetic field? How much magnetic field do I have times the area it's covered? Okay, now we have cosine theta because we're looking at the perpendicular amount, right? Because we care about how much is perpendicular to the area. Because if it's parallel, then it would be 0. So we're looking at perpendicular, so we use cosine instead of sine. So the stronger the field, the more flux. The bigger the loop, the more flux. So the bigger the area, the more flux. The symbol for flux is this phi symbol, and the measurement is Webers. I like this unit. I think it's fun. Webers. WB. So let's look at an example. We have this equation here. Flux equals BA cosine theta. So a 0.3 magnetic field is directed perpendicular to the loop of a wire with a radius of 0.0025 meters, because it's 0.25 centimeters. So your area equals pi r squared. So pi times 0.0025 squared times cosine of 30. So we're looking for the change in flux. So initially, we're going from cosine with a radius of, let me see, what is it? It's directed perpendicular. So at first we're going from cosine of 90, which is 0. So we're going from 0 to whatever it is for cosine of 30. So 0.3 times pi times 0.0025 squared times cosine of 30. So our flux went from 0 to 5.1 times 10 to the negative 6th. So this is our change in flux. Now when you change your flux, when you change your magnetic field, you induce a current or an EMF. Changing the amount of flux produces a current or an EMF. EMF is another word for voltage or potential difference, that kind of thing. So we produce an EMF, which is then pushing a current. So changing the flux produces an EMF, which produces a current. One way to induce an EMF is by moving a conductor through a constant magnetic field. This is known as motional EMF. Now if you want to play with this and check it out, you can search PHET, P-H-E-T, and this is Faraday's Electromagnetic Lab. I'm on the second tab, and this is going to show you motional EMF. So I move this through the magnetic field, and it produces a current. It produces an EMF, which produces a current. Okay, I can do the same thing by moving that. Okay, so changing that magnetic field, moving the magnetic field through it, produces an EMF. This goes along with Faraday's law. Faraday's law is an equation that represents the mathematical relationship between induced EMF and change in flux. Okay, so you have this EMF. So you produce this voltage, potential difference. Alright, and it depends on your change in flux over time. So if we bring this back up, you move it real slow, you get little light. Move it real fast, get lots of light. Okay, so that's what this is all about. And it's a negative. Okay, so it's the opposite direction. Now, if you have more than one loop, then you have to also multiply by n, where n is the number of turns of wire. And as your number of turns of wire goes up, so does the EMF. And if you went to that simulation online and you could change the number of coils, and you'll see what it means. Now, one of the favorite examples that they have on the AP test, and I saw at my college love these examples, is when you change the area. So you have this wire, or this conducting thing going around, and then you have another conductor connecting them. And this wire can slide up and down. So you slide it up, right? Increasing the area. By increasing the area, you create a change in flux, which produces an EMF. Okay, so BL change in X. So basically you're changing your area, and it breaks down to be BLV. And you end up with E equals BLV, which is in your reference table, which is nice. But the BLV comes from BL times V, which is X over T. So it's kind of like this equation simplified down to the change in area. The negative will drop off for now. We'll talk about directions soon. Alright, let's look at an example. You have 25 turn coil, has a diameter of 1, so a radius of 0.5. It is placed with its axis in the direction of the Earth's 50 micro, so 50 times 10 to the negative 6 Tesla magnetic field. And then in 2 seconds, 0.2 seconds, excuse me, it's flipped 180 degrees. What is the average EMF? So average EMF equals change in flux divided by change in T. Now this is not the one where we use X and T because we're not changing the area. So we're using our other flux equation, which is negative BA cosine theta over T. Now, the only thing that changes, because we're looking for the change, B doesn't change, A doesn't change. The only thing that changes is cosine theta. So you get the change of cosine theta. So it's cosine of 180 minus cosine of 0. Which becomes cosine of 1 minus negative 1. So E equals 50 times 10 to the 6th times your area, which is pi times 0.5 squared times negative 2, positive 2, divided by 0.2. And all you have to do is plug it into your handy dandy calculator, and you should get 3.9 times 10 to the, let's see, 8th. 3.9 times 10 to the 8th equals your induced EMF, and that's in volts. Okay, next we have Lenz's law. Lenz's law allows us to determine the direction of the induced current. So what direction are we going to induce the current in? An induced current will be directed in such a way that the magnetic field that it produces is the opposite. This goes along with Newton's first law. Things don't want to change. They want to stay the way they are. So if you have a magnetic field that's going this way, well, you're going to produce a magnetic field going this way to counterbalance it, to make it, you know, back to its normal, everyday, previous state. Now, I really like this simulation. Okay, see how you have this North Pole coming in, and the arrows are pointing in, and it induces a magnetic field in the opposite direction. You see how that works? I thought that was a real nice demonstration. Okay, here's another set of pictures. So you push this N through, or this North Pole through, so the magnetic field's going this way. It's going to induce a current such that a magnetic field is produced this way. And if you use the second right-hand rule, your thumb, or your fingers are going to point that way on the inside, right? So your fingers are going to curl, so this is the direction of the magnetic field on the inside, causing your thumb to create a current. So if we go over here, we see that we induce a current in this direction. So your fingers loop this way, pointing your thumb up this way. Or your thumb points this way, so your current flows this way. Okay, so it kind of cancels each other out. They're looking to try and cancel. Same idea with a solenoid, same type of thing. Alright, North Pole comes in. It's going to create a current such that your North Pole points that way. And you can use the third right-hand rule to figure that out. Okay, that's the end of the lesson. Good luck on your homework.